Welcome back. Today, we're diving into something that is absolutely going to flip how you think about self-driving cars. It's so easy to just assume they look at the road the same way you and I do, just through the lens of a digital camera, right? But the reality? It is so much more complex and honestly, mathematically fascinating. We are pulling back the curtain on what I like to call the illusion of sight. But hey, before we even touch on vision, we've got to talk about time. Because in this world, time literally equals physical distance. Picture this, a car cruising down the highway at 120 kilometers per hour. At that speed, every single 100 milliseconds of computer processing delay adds 3.3 meters of distance before the car even begins to react. So think about what that actually means on the road. If the software gets bogged down, maybe by too many heavy high-res camera feeds or just unoptimized neural network code, that vehicle is effectively blind for those 3.3 meters. It's hurtling forward through physical space, but its digital brain, it's stuck in the past. In the realm of physical AI, that perception to action loop has to be instantaneous. A 100-millisecond lag isn't just an annoying buffering screen, it's the absolute difference between a safe stop and a total disaster. Okay, let's dive right into our first major concept, the probability fallacy. Keeping that strict time limit in mind, let's look at how AI actually processes its environment. Look at this normal hallway right here. When you or I look down this hall, our brains instantly, effortlessly map it out, right? We see the walls, we spot the door at the back, we notice the potted plant sitting there on the left. No conscious math required, we just know what those objects are. We take that absolute certainty completely for granted. Now, what's really interesting about this slide is that an AI's perspective is basically an entirely different universe. Autonomous cars do not actually see a potted plant or a backpack as discrete physical objects. Look at these bounding boxes and those glowing spatial uncertainty heat maps. The AI is basically saying, hey, I am 99% sure there's a cluster of pixels right here that statistically matches a plant. And here's a heat map showing exactly how confident I am about its physical edges. It's not sight, it's high-speed statistical guessing. Which brings us to a really fascinating metric engineers use, called probability-based detection quality, or PDQ. Unlike human vision, PDQ evaluates the quality of uncertainty, both spatial and label uncertainty. It doesn't ask for absolute truth. Think of the AI's probabilistic vision like a human trying to make out shapes in a pitch-dark room. If the shadows suddenly shift, or if there's random noise from the sensors, the confidence in that shape drops off a cliff, and the car might hesitate. It's constantly guessing, adjusting, and recalculating those confidence scores multiple times every single second. So, what happens when it guesses wrong? That brings us to section 2, the edge case problem. Seriously, what happens when that probability dips drastically because the car encounters a totally untrained situation? We can look at the official recounting of a tragic 2016 collision involving a vehicle on autopilot. The investigation literally noted that neither the autopilot system nor the driver noticed the white side of a tractor trailer crossing the highway against a brightly lit sky. Because of the trailer's height and that glaring white background, the AI's probability scores just failed. It completely lacked the fundamental logic to separate a white truck from a bright sky, resulting in a devastating failure to apply the brakes. And that right there is a prime example of the danger of the long tail of data. Look, if you train an AI on millions of miles of sunny, predictable highway driving, it's going to be an absolute genius in that specific environment. But it might completely lack the logic to handle rare visual overlaps, or weird weather, or say, a stationary emergency vehicle parked at an odd angle in the middle of the night. The model performs beautifully on average, but it can fail catastrophically in these long-tailed, safety-critical edge cases. Okay, so how do engineers fix this? Let's move to section 3, sensor fusion, basically the car's built-in voting mechanism. To stop these isolated visual failures from causing crashes, engineers introduce a high-speed voting committee for the car's brain. First, you've got the camera. Awesome for color and semantic detail, but easily blinded by glare or darkness. Then you have LiDAR, which shoots out lasers to get incredibly precise shape and depth data, but it can get severely degraded by heavy rain. And finally, radar, which cuts right through bad weather to measure speed and movement, but has super low resolution. And this brilliantly illustrates how they work together. If the camera is blinded by the sun, like in that 2016 edge case, the LiDAR and radar have to independently cross-check each other and vote to confirm that yes, there's absolutely a large vehicle ahead. And when researchers purposely mess with the camera streams, like blurring the lens or cutting off the field of view, a solid redundancy-aware sensor fusion system steps up. We actually see mean intersection over union, basically perception accuracy, jump by roughly 0.08 to 0.22. Now that might sound like a tiny mathematical bump, but that bump is literally the difference between the car entirely losing track of a hazard and safely maintaining a continuous understanding of its environment while a main sensor is actively failing.
But we've got to go deeper. Section 4, fail operational safety nets.
Because we have to push this to the absolute limit. What happens if the entire primary perception stack just completely dies? So the crucial point is the architectural shift from fail silent to fail operational. In older Level 2 driver assist systems, if something failed, it just beeped loudly and dumped control right back in your lap. But a Level 4 fully autonomous vehicle, it has to manage the disaster autonomously. In under 100 milliseconds, tying right back to that latency physics we started with, if the main system crashes, an arbitration unit instantly swaps the control chains. A totally independent backup system takes over and executes a minimal risk maneuver, smoothly pulling the car over to a safe stop without any human intervention.
Honestly, it is a breathtaking symphony of modern engineering. We've journeyed all the way from the strict physics of processing latency through the wild mathematical guesswork of probabilistic vision and edge cases, straight into sensor voting and split-second backup architectures. Which leaves us with one final, incredibly important question to ponder. As these self-driving systems rapidly scale up and hit our roads, can we truly trust probabilistic machines with human lives? It is a razor-thin balance between latency and mathematics, and perfecting it is going to be the defining challenge of our era. Thank you so much for exploring this with me today. Keep questioning what you see.